Hi. In this video, so this is third video for our course, and in this one, we'll discuss properties of GCD and LCM. So I'm sure you're already aware of what greatest common divisor or HCF and LCM are, and we'll see some properties. Before we start, we'll look at the definition. So for a positive integer k, for a positive integer k, let's say d of dk is the set of all possible all its positive divisors. Divisors or basically factors. So obviously dk is a finite set because the number of possible factors or divisors of a positive integer is going to be finite. So for positive integers m and n, we can call the maximal element in the set dm intersection dn is known as GCD, is the GCD of m and n. So let's try to understand what this means. So if you have two positive integers m and n, you can construct their own divisor sets, right? dm is the divisor set of all divisors of m, and dn is set of all divisors of n. Now, if we construct this set dm intersection dn, we are basically doing what? Divisors which are present in both the sets. So basically, these are common divisors or common factors. And once we have this set of common divisors, we are just selecting the highest common factor or greatest common divisor, right? So when GCD of the two numbers m and n is equal to 1, then that means that m and n are relatively prime or co-prime. Relatively prime or co-prime. Basically, they don't have any common factors. If your GCD of two numbers is 1, they don't have any common factors. Now let's look at some properties here. So the first thing is, if D is equal to GCD of m and n, then we can write m is equal to d times m dash and n is equal to d times n dash, right? Because d is one of the divisors, right? So basically m can be written as d into some m dash, and n can be written as d into some n dash, where m dash and n dash are integers. And then we will have the GCD of m dash and n dash must be equal to 1, right? So basically what this means is, if D is the GCD of m and n, then from m and n, if we divide D, then basically we have taken out the factor highest common factor, right? So the remaining part will definitely have no other common factors. So therefore what we are saying is, whatever remains when we remove D from m and n, which is basically m by D and n by D, that number, these two numbers will be co-prime to each other, right? So it should be fairly obvious. Now, let's say we have, if D dash is a common divisor of m and n, then we know D dash divides GCD of m and n. Why? Because GCD of m and n is the highest common divisor, right? Highest common factor. So D dash was one of the factors, then obviously that one of the factors will divide the highest common factor, right? So this is first property. This is the second one. Now, this third property says that how to find the GCD of two numbers given its prime factorization. So if m is p1 power alpha 1, p2 power alpha 2, and so on, will pk power alpha k, and similarly n is p1 power beta 1, p2 power beta 2, and so on, till say pk power beta k, right? Now, GCD of m and n will be equal to p1 power minimum of alpha 1 comma beta 1, p2 power minimum of alpha 2 comma beta 2, and so on till pk power minimum of alpha k comma beta k. So basically, amongst once you have the prime factorization, you should be quickly able to find the GCD, because what you will do is take the lowest common power. So for each prime factor, if the powers are alpha 1 and beta 1 in the two different prime factorizations, you take the lower power, because obviously that lower power is definitely there in both of them, right? It could be zero also. There might not be no power there. So you'll get p1 power 0 when you do minimum of alpha 1 and beta 1. But this is a standard method to find basically your GCD in case you know the two numbers and their prime factorization. What if the numbers are big, and their prime factorizations are hard to obtain, right? In that case, we have an algorithm, which is the Euclid's GCD algorithm. So we'll say that if m is equal to nq plus r. So basically, what we have done here is written m as the product of n and q plus r, because this is just m divided by n. You're doing division of m by n, and you're getting quotient q and remainder r, right? Then we have GCD of m and n is equal to GCD of n and r. Okay. So how do we know that that is true? So we know that if let d let d be the GCD of m and n, right? So that means that d divides m and d divides n, right? So so that will imply if d divides m and d divides n, then obviously d should divide r, right? Correct? Right. And here we have let d dash let d dash be the GCD of n and r, right? So that means that d dash divides n and d dash divides r, correct? That implies that d dash should divide m, right? Why? Because if d dash divides this and this, then obviously d dash divides m, right? And now what we want to get here, we want to prove that d dash is equal to d, right? This is what we want to prove. So how do we prove that? So in order to prove that, since d dash divides m, therefore d dash divides d, right? Because d dash is a factor of m and d is the highest common factor of m and n. D dash is a factor of m and n. So D dash is one of the common factors and D is the highest common factor. So D dash divides D we get from here, right? Now, if we can prove D divides D dash, then we will be done, right? So now notice that here we have D divides N and D divides R, right? These two statements. So D is a common factor of N and R. Therefore, D will divide D dash, which is the GCD of N and R, right? So one side we have D divides D dash, because D is a common factor of N and R, and highest common factor of N and R is D dash. That's why. And the other side we have D dash divides D, because D dash divides R and D dash divides D. And Actually, d dash divides r and d dash divides n implies that d dash divides m, and now you have d dash divides m and d dash divides n, which implies that d dash divides d, because d dash is the common factor of m and n. So, and d is the highest common factor of m and n. So, since we have gotten the two cases that d divides d dash and d dash divides d, this implies that d is equal to d dash, right? So basically, we have proved the result for Euclid's GCD algorithm. And now we'll just learn about how we will go about finding the GCD of two numbers. So let's do it on the screen. So let's say you have m, and when we divide by n, we get nq1 plus r1, right? And obviously 1 is less than equal to r1 is less than n, right? Now the next step that we do is we take n and divide by r1, right? We take n and write it as r1 multiplied by q2 plus some other remainder r2. And obviously again r2 is less than equal to r1, right? So what are we doing? First step was at m by n. Second step was n by r1. Third step will be r1 by r2. Third step will be this. So we'll write it like this: r1 is equal to r2 q3 plus r3, right? Correct. So similarly, we'll keep doing it till we reach this stage. Rk minus 2 is equal to Rk minus 1 q of k plus Rk, right? And finally, we will say Rk minus 1 is equal to Rk q of k plus 1 plus R of k plus 1, right? This final division we'll keep doing till we reach the point where Rk plus 1 is 0. Everywhere else we'll get inequalities like this. So we are writing inequalities like this, and at the end you should have Rk plus 1 is equal to 0, right? Now what we will say here, from the first step, we can say that GCD of m and n, GCD of m and n is equal to GCD of n and r, and n and r1 actually, because we labeled it as r1, and that GCD of n and r1 will be equal to GCD of r1 and r2, which will be equal to GCD of r2 and r3, and so on. This chain continues till we get equal to GCD of rk minus 1 comma rk, right? And here, since we in this step we got Rk plus 1 is 0, what this means is Rk minus 1 is divisible by Rk, right? Like completely divisible by Rk. This remainder turned out to be 0, right? Therefore, the highest common factor or GCD will be equal to, this GCD should be equal to Rk, because Rk minus 1 is divisible by Rk. So basically, the last non-zero remainder in this chain, is the is GCD of m comma n. So what are we doing? We are doing repeated division till we get to the point when the remainder came out to be 0. Repeated division in what way? You're dividing m and n, you're getting n q1 plus r1. Then you're taking n and r1, and you're dividing those. So n will be equal to r1 q2 plus r2. And then you will divide r1 and r2. And so on. You keep doing till you get a 0 remainder. The last non-zero remainder is the HCF or the GCD. This one, right? How are we getting it? We are getting it using the property that we just proved on the previous screen, where GCD Mn is equal to GCD Nr, right? If M and N are any two numbers. So this is your Euclid's GCD algorithm. Now let's look at another property. We say that for any, this is a very important one. So just keep this in mind. For any positive integers, for any positive integers, m and n, m and n, there exist integers a and b such that ma plus nb will always be equal to GCD of m and n. This is sometimes known as Bizot's lemma, and this is quite important. So how you can prove this is actually, like, since you are finding m and n, so you can do the Euclid's division algorithm and say m is equal to nq plus r, and you keep doing this chain of things. So you'll say q is equal to, no, r, n is equal to rq1 plus r2, and so on. And you reverse all the steps in order to write. Eventually you should get something like this, right? You'll get rk minus 1 is equal to rk qk plus 1. That's it, right? So what we can say is, what are the integers ma plus nb which is equal to GCD of mn? Now here we know that GCD of mn will be the previous step remainder, right? You know, rk minus 2 is equal to rk minus 1 q of k plus rk. Rk is the remainder here. Rk is equal to GCD of m and n, right? So what we can say is rk is equal to rk minus 2 minus rk minus 1 into qk, right? So we are writing your GCD here. GCD mn is equal to rk minus 2 minus rk minus 1 into qk, right? And now you can say that rk minus 1 will come in this equation, right? And substitute for that equation here. So you will keep going higher and higher in this chain, right? And rk minus 2 also you can substitute as, yeah, you keep going higher and higher in this chain, and you will start getting back to m and n basically. Eventually you'll get m and n somewhere, right? So we'll see examples of this later, where we express the GCD in terms of the individual numbers, a linear combination of the numbers m and n. Basically, what we are saying is, if 2 and 3 are two numbers m and n, we know that the GCD of 2 and 3 is equal to 1. So there will be integers such that 2x plus 3y is equal to 1, right? So we can always find such integers. So x is equal to 2 and y is equal to minus 1 obviously is a pair, which will give x is 2, y is minus 1. Basically, x and y stand for a and b here. You will always be able to find a solution of this equation, basically, right? So that is Bizot's lemma. The proof of this can be just reverse all the steps in the Euclid's GCD algorithm. Reverse all the steps, start from the bottom, and keep expressing all of the RKs in terms of the previous equations. Now, let's look at what is LCM. What is the meaning of LCM? So for integers k, again, we will say for integers k, the set mk is the set of all the multiples of k. Set of all multiples of k. Now, obviously, this is an infinite set because you can keep making new multiples which are larger and larger, right? Now, if you have two integers, if we have two integers s and t, then the minimal element of the set ms intersection mt is equal to LCM of S and T. So what are we doing? We are constructing the set of multiples of S and the set of multiples of T, and we are taking the least common element present in both the sets, right? Least common element in the sets will be the least common multiple, right? So now let's look at some basic properties of LCM. So we have, if M is equal to LCM of S and T, then what this means is M is equal to S into some S dash, and M is also equal to T into some T dash. Then we have GCD of S dash and T dash should be 1. The S dash and T dash numbers should be co-prime, because if not, what will happen is S dash and C dash, if they have a common factor, then that common factor could have been used to get a higher LCM, right? Correct. So if they have a common factor, that common factor could have been included outside, and you will have a higher, basically, LCM for these two, right? So if M is the LCM of S and T, for example, let's take an example like, you have, let's say, 6 and 15. 6 is equal to S, T is equal to 15. Now, we know that the multiple of 6 multiples are 6, 12, 18, 24, 30, and so on, right? And 15's multiples are 15, 30. So obviously the common multiples start from 30, right? And the least common multiple M should be equal to 30 for these two, right? Now you can easily say that 30 is equal to 6 into 5 and is also equal to 15 into 2. Now notice that 2 and 5 have no common factors, right? 2 and 5, if they had a common factor, you could actually have taken that common factor out and you would have gotten a smaller value of a LCM, right? So if this was some AB and this was some BC, 6AB and 15BC, you would have said 30 is equal to this is equal to this. So I could have instead said 30 by B is my LCM, right? Least common multiple. Because then that would have been 6A and it would have been equal to 15C. So we are still getting 6 and 15's LCM, right? But it would have been 30 by B instead. So if your GCD of S dash and T dash is not 1, your LCM will be lower, right? So that is one property that is important. Then we look at the standard result that you are probably already aware of for any two positive integers. For any two positive integers, M and N, we have GCD of M and N multiplied by LCM of M and N should be equal to M into N. The reason for this is obvious if you think about the prime factorization of M and N and find out the LCM from there. LCM of two numbers is going to be the higher power of the prime numbers, right? So it will be P1 maximum of alpha 1 beta 1, P2 maximum of alpha 2 beta 2, and so on. Pk is maximum of alpha k and beta k. So this will give you the LCM. Notice that in the HCF portion, what we did was we take the minimum power. Now we are taking maximum power because LCM should always be greater than the original number, right? Now, I'll just restate one standard result that we already seen. Let A, B, X, Y are integers, N are integers such that AX plus BY is equal to N, right? Then we can always show prove that GCD of A and B divides N. GCD of A and B divides N, right? So basically, this is like saying that this is basically the statement of Bezot's lemma. So it says that this equation has a solution in integers only if N has a factor which is GCD of A and B, right? So another another property that we can see here is if C divides AB, C divides AB and GCD of C and A is equal to 1, then C divides B. So it's obvious why this is true. C divides A and B. So either A is divisible by C or B is divisible by C. But here you are getting GCD of C and A is 1. So basically they don't have any common factors. So then that means that all the common factors for C must have come from B, right? If C divides A and B, it's either C is dividing A or it is dividing B. If GCD C of A, C comma A is 1, that means C is not dividing A and therefore C must be dividing B, right? Otherwise, how will the original condition be true? C divides AB. So this is quite important. We can prove this in a simple way. We say that GCD of C and A is 1. Therefore, there are integers x and y such that Cx plus Ay is equal to 1. This is from Bizot's lemma. Now, if we multiply both sides by b, cbx plus aby is equal to b, right? Now, here we know that c divides cbx and c divides ab. So that implies c divides aby. So LHS is divisible by c. That implies obviously that b, c divides b, right? RHS must also be divisible by c, correct? Right. So this is basic stuff and basic theory of GCD and LCM that you need to be aware of for your IOQM, RMO and stuff. Then what we will continue with in the next class is we'll start our journey and start looking at modular arithmetic. So don't stress out about more properties for GCD and LCM. Like the properties that we have so far discussed are more than sufficient to solve your Olympiad problems. You don't need any fancy properties here. Once you understand this much and have practiced enough questions that you can apply this intelligently in problems, then this much theory is actually enough. There's nothing needed to go beyond this level. Uh, we'll continue with modular arithmetic in the next video. After that, we'll do a few theorems or few standard theorems like Wilson's theorem and Fermat's little theorem and so on. And eventually we'll look at arithmetic functions. So 3-4 theory lectures are still there. Once we are done with that, we'll focus entirely on problem solving in this course. So stay tuned and I hope you're learning a lot from these lectures. See you next time.